Hello students, welcome to another video of metric space. Today we will discuss some examples of sequences and after that our completeness. So the first example is let x and y be two metric spaces let x cross y be a product metric space, be a product of metric space, that is be a product metric space, then show that sequence xn yn. So this is the sequence in product metric space x cross y. We have seen the product metric space in the first chapter, that is if x and y are two metric spaces, then x cross y is also a metric space, and which is defined as distance between x and y is equals to maximum of distance x and x, y and y. So we will see that in the solution. So show that this sequence x and y n, this is one sequence in this product metric space x and y n, in this is sequence in x cross y converges to, this sequence converges to order pair xy, xn yn, this is sequence in x cross y, and that sequence in x cross y again converges to a point in x cross y. So this x and yn converges to xy if and only if this sequence xn converges to xn converges to this x in x, and this yn converges to this y in y, if and only if this xn converges to x in metric space x, and this sequence yn converges to this y in y, yn converges to y in y. This is the example. So here we have given that x and y be any two metric spaces and x cross y be a product metric space, and we have to show that a sequence x and yn, a sequence in product metric space x and yn converges to a point, that is a order where xy in x cross y if and only if this xn converges to x in x and yn converges to y in y. Now first of all we will suppose this xn converges to x in x and yn converges to y in y, and we will prove this xn yn converges to order pair xy, and conversely we will suppose this order pair xy converges to xy, and the order pair x and yn converges to xy. After that we will prove this xn converges to x and yn converges to y. Now suppose this xn converges to x in x and the sequence yn converges to y in y. Now therefore by definition of convergence we can write for any epsilon positive there exists some n belongs to natural number. Suppose this capital N1 belongs to set of natural numbers such that distance between x and xn, this xn converges to x means distance between x and x or x and xn is less than epsilon for all n greater than or equals to n1. Similarly this yn converges to y. So again we can use, suppose this is equation number 1, also this yn converges to y, therefore and for epsilon positive there exists n2 belongs to set of natural numbers such that this distance between y and yn is less than epsilon for all n greater than or equals to n2. Suppose this is equation number 2. Now similarly like previous example we can take the maximum between n1 and n2 so that both the conditions are satisfied. So choose capital N is equals to maximum between n1 and n2, maximum of n1 comma n2. Therefore, this distance between x and x is less than epsilon, distance between y and yn less than epsilon for all this n greater equal this n. Distance between x comma xn is less than epsilon, and distance between y and yn is again less than epsilon for all n greater than or equals to n. Now, this implies that maximum of distance between x xn y yn is less than epsilon, because both are less than epsilon, and if we take the maximum between these two, then clearly this is again less than the maximum between these two, again less than epsilon. This implies maximum of distance between x xn comma y yn. This distance between x xn less than epsilon, also distance between y and yn is again less than epsilon. So, maximum between these two is again less than epsilon. Maximum of distance between y and yn is less than epsilon. This is maximum between these two is again less than epsilon for all n greater equal n, for this all n greater equal n. So, this is maximum of distance x xn, distance between y yn is less than epsilon, implies this is the definition of product metric, that is distance between this xn yn comma x and y, distance between this xy comma xn yn is less than epsilon. This implies distance between xn yn comma distance y, distance between xn yn and xy is less than epsilon for all n greater equal n. This is the definition of metric in product metric, that is distance between xy, x1 y1 x2 y2 is equals to maximum distance between x1 y1 x2 y2. This is the definition of metric on product metric space that we have seen in the first chapter. This is by definition of D on product metric, by definition of D on product metric. So, this implies distance between xn yn and xy is less than epsilon, means this xn yn converges to xy. This is the definition of definition of convergence of sequence. Here this sequence is in x cross y and this is a point in x cross y. So, this sequence in x cross y converges to this point in that x cross y. So, this implies the sequence xn yn converges to order pair xy. Hence, the first part is proved. In the first part, we have supposed this xn converges to xn x, yn converges to yn y, and our claim was xn yn converges to xy. So, xn yn converges to xy is proved. Now, conversely, we will suppose that this sequence xn yn converges to order pair xy. This is in product matrix space x cross y. Now, again by using definition of convergence, we can write for given epsilon positive, there exists some n belongs to set of natural numbers such that distance between xn yn and this xy, that is this is the definition of product metric, distance between xn yn comma order pair xy is less than epsilon for all n greater equal n. This is by using definition of product metric in this is the definition of D on product metric. Now, by using definition of D in product metric, we can write maximum of distance between x and x comma distance between y and y is less than epsilon. Distance between x and x comma distance between yn and y is less than epsilon for all n greater than or equals to n. Sorry, this is just a capital N. This is by using definition of D on product metric. Maximum distance between x and x, y and y is less than epsilon for all n greater or equal n. So, this implies that maximum of these two distances is less than epsilon. So, clearly the another distance maximum of these two, that is suppose this is 10 and this is 15. So, that 15 is less than epsilon. So, clearly again 10 is less than epsilon. If the maximum between these two is less than epsilon, then clearly these two distances are less than epsilon. Therefore, we can write distance between xn and x is less than epsilon, and distance between yn and y is less than epsilon for all n belongs to, for all n greater than or equals to n. Now, distance between xn and x less than epsilon, again distance between yn and y less than epsilon for all n greater or equal n, implies that this xn converges to x and yn converges to y. So, we can write the sequence xn converges to x in x and the sequence yn converges to y in y. Hence, the proof of, hence the solution of the given example. Now, the next example is when does the sequence in discrete metric space converges? When does the sequence in discrete metric space converges? This is important question for 2 marks. When does the sequence in discrete metric space converges? We know that the sequence xn is converges to some element in that metric space, then we can use the definition of epsilon n definition. So, if we take, we have given that, we have to prove that when does the sequence in discrete metric space converges. If we suppose x be a discrete metric space and xn be any sequence in that x, and we suppose that xn converges to x, then we can use the definition of convergence, and after that we will see the convergent, that is the limit of that sequence. So, we will take xd as a discrete metric space. Let xd be a discrete metric space and this sequence xn be a sequence in x. Let xn be a sequence in that x such that that sequence xn converges to x, that is some element in x. Therefore, by definition of convergence, we can write for epsilon positive there exists natural number n belongs to natural numbers such that this distance between xn and x less than epsilon for all n greater or equal n. Distance between x and xn is less than epsilon for all n greater or equal n. This is by definition of convergence of limit, and this distance between x and x is less than epsilon. Epsilon is very small, so this distance between x and xn is less than epsilon is possible only when the x and x are equal, that is their distance between these two numbers is equals to 0. In discrete metric space, we know that distance between any two points is defined as either 0 or 1. 0 only when these 2 points are equal and 1 elsewhere, otherwise the distance is 1. So, epsilon is very less number, that is very epsilon is tends to 0. So, for any number tends to 0, distance between x and xn is possible distance between x and xn is equals to 0. So, for epsilon, very smaller epsilon, that is if you take epsilon is equals to 1 upon 1000, then that epsilon is very close to 0. But if we take that epsilon, then distance between that x and xn is less than suppose 0.001. It is possible only when these two are equal, that is distance between x and xn is equals to 0, because in discrete metric space there are only two possibilities for the distances, either 1 or 0. 1 whenever these 2 points are different, and 0 only when these 2 points are equal. So, we have to take distance between these 2 points is less than epsilon, and epsilon is always tends to 0. So, for this distance less than epsilon, there is only one possibility to the distance which is 0. So this is possible only when this distance between x and xn is less than epsilon is possible only when x and x are equal, only when distance of x and xn is equals to 0 for any epsilon greater than 0, for any epsilon greater than 0. So this implies distance of x and xn is equal to 0 means x is equals to xn for all n greater equal n, if it for any n greater equal, that is all the terms except finite many points. So sequence in metric space, in discrete metric space is convergent only when x is equals to xn. So if we take any sequence in discrete metric space, and we can say that sequence has limit x whenever all the points are equals to x. So metric space convergence in discrete metric space, sequence is convergent in discrete metric space only when x is equals to xn for all n greater equal n, for all n belongs to natural numbers. So this is the solution. Now the next topic is Cauchy sequence and completeness. So next point is Cauchy sequence and completeness. Cauchy sequence and completeness. First of all, we will see the definition of Cauchy sequence. So first topic is definition of Cauchy sequence. Definition of Cauchy sequence. So in this topic we will see the definition of Cauchy sequence, and in the next video we will see some theorems on that. A sequence in metric space is said to be Cauchy. A sequence in metric space is said to be Cauchy sequence, is said to be Cauchy sequence. Same definition as you have seen in the real analysis, is said to be Cauchy sequence if for any epsilon positive, there exists some n belongs to natural number such that distance between xn and xm, is less than epsilon, for all m comma n greater equal n. A sequence in metric space is said to be Cauchy if for any epsilon positive there exists n belongs to natural number such that distance between xm and xn is less than epsilon for all mn greater equal 0. So the sequence is said to be Cauchy if for all mn greater equal 0, for larger values of m and n, the two numbers of the sequence are very close to each other. That is, this xn less than epsilon means epsilon is very small number. So for the larger values of m and n, so if our sequence is x1, x2, x3, x4 up to suppose x100, x1000 and so on, so for the larger values of x, that is suppose x1000 and x1000 plus 1 are two numbers of that sequence, then the distance between these two numbers is very less. For example, if we take xn is equals to 1 upon n, then for larger values of this n, the numbers are very close to 0. So different distance between that numbers is very less. Suppose if we take 1 upon suppose this number, and if we take the another number as 1 upon this 0. This number, so there is a very small distance between these two numbers. If you take these two numbers of this sequence, then for this there is a very small difference in between these two numbers. So distance between these two numbers is very less, that is less than epsilon. So then this sequence is said to be Cauchy sequence. A sequence in metric space is said to be Cauchy if for any epsilon positive. If you take any epsilon, if you take epsilon is equals to 1, 0.001, 0.0, very small epsilon, then for that epsilon, distance between these two numbers, distance between xm and xn, two numbers of that sequence, two elements of that sequence is very close to each other. That is, distance between the two elements of that sequence is nearly equals to 0. Then we say that the given sequence is Cauchy sequence. If we take xn is equals to 1 upon n in the closed interval 0 1, this closed interval 0 1 is a metric induced from standard metric, then for that metric 1 upon n is Cauchy sequence. This is for example. There is no need to write this example in your notebook. So this is the definition of Cauchy sequence. Now we will see some theorems in the next video.